All right, so let's go ahead and talk about the common ion effect. So one of the big takeaways from here is that we're going to be able to use Kas and Kbs and then start to think about whether we have an acid or a base reaction, and then just use what we've learned previously with equilibrium constants to determine which direction a reaction is going and what our products will be. So these are really important whenever we start to talk about biological systems, because if you have a weak acid or conjugate base system, so if we had like acetic acid and sodium acetate, even if you add acid or base, they are going to resist large changes in pH. So this is ideal for biological systems where you don't want to, after you eat a bag of salt and vinegar potato chips, you don't want your pH to start to drop to acidic and shut your body down. So what we're going to do here is we're going to look at the process of mixing acetic acid and then acetate. So species that would be present would be our acetic acid. Then if we had sodium acetate, so we'd have our sodium ion and then our acetate anion from whenever those dissociate, and then we'd end up with water, which can behave as either an acid or a base. So what we'll look at is if we add acetic acid and sodium acetate, we're just going to have a proton transfer back and forth. So whatever acetic acid dissociates is going to end up reforming whenever that proton is transferred from here to here. The other thing that we need to consider is the reaction of just the acetic acid itself dissociating. So if we have acetic acid acting like our acid, water acting as our base, then we could have a proton transfer and end up with the hydronium ion and then the acetate ion. And we're really going to look at this and try to use Le Chatelier's principle, but I'm going to show you how you can use Ka and Kb as well. So for the first example, if we add acetic acid, so if we increase the concentration of acetic acid, which direction is the reaction going to go? Let's go ahead and write out our acid dissociation constant. So we'll have Ka is equal to H3O plus times our acetate divided by our acetic acid. So if we add acetic acid, Le Chatelier's principle says this reaction is going to go to the right. If we add acetate, what we'll see is this reaction is going to go to the left, assuming that this was at equilibrium initially. So you can think about it in the same way. So what we're going to do is we're going to go ahead and start to think about some of these weak acid and weak base conjugate systems. Now these are the ones that are most common whenever you have acetic acid or acetate, where you have hydrofluoric and then the fluoride ion. We have ammonium and ammonia, and that's typical for a base, a conjugate base, and then a conjugate acid system. And then we'll have our hydrogen phosphate ion. Let's go ahead and consider acetic acid. So here we want to find the pH of a weak acid of a 0.1 molar acetic acid and 0.1 molar sodium acetate. So we left sodium off because sodium ends up being a spectator ion. Let's go ahead and set up our ice chart like we have in the past. We'll plug in our initial concentrations for acetic acid and for acetate. We know that water does not contribute to our equilibrium constant, and then H3O plus was initially 0. So since H3O plus is 0, this means our Q value is equal to 0 because the numerator has a 0 value. So our reaction is going to proceed to the right. So that means this will be minus X plus X plus X. Now we have 0.10 minus X, X, and then 0.10 plus X. Okay, so if we end up writing our expression for Ka, so Ka is going to be equal to products over reactants. So we'll have X times 0.10 plus X all over 0.10 minus x. Okay, and then we know that Ka for acetic acid is equal to 1.8 times 10 to the negative fifth. Alright, so I'm going to teach you a trick now, and that is, if this Ka value is going to be 3 or more orders of magnitude different from x, or sorry, not different from x, different from the initial concentrations, we can actually ignore x. Because once we go through and distribute, so multiply the denominator by 1.8 times 10 to the negative fifth, and then we have the numerator being 0.1x plus x squared. What we're going to see is that this x value is essentially going to be negligible compared to 0.10. So you should try to solve it out the long way and then prove that my shortcut way will work as well. So what we're going to see is if 0.1 is the initial concentration of acetic acid and acetate, that this x value can just go away, because these values are 1 times 10 to the negative 1, whereas the Ka value is 10 to the negative fifth. Well, these values are greater than 3 orders of magnitude from each other, so we can ignore x. So then our expression ends up being, well, 0.1 divided by 0.1 is 1, so x equals 1.8 times 10 to the negative fifth. And if you graph this out or use the quadratic equation, you will also get the same answer for x after you round it. There's a very small deviation from that value. Alright, so since that's our x value, we can find pH. So pH is going to be equal to the negative log of the hydronium concentration. So in that case, 1.8 times 10 to the negative fifth, which equals 4.7, which would be the correct number of sig figs, but just for comparison later, I'm going to go ahead and say that it's 4.74, and I'll put that 4 in parentheses. Well, what's special about this conjugate acid-base system? Well, if you have equal concentrations of your acid and your base, remember that x equals your Ka. So that means that pH equals your pKa whenever these two concentrations are equal of your acid and your conjugate base. Alright, so now let's go ahead and show how whenever we add a base or an acid that there's very little effect. So I've already worked this out, but I will show you how we go about doing this. So the first thing that you want to do is we want to go ahead and look at what the change in concentration was. So we'll look at adding hydroxide. So if we have 0.1 molar acetic acid, we have 0.1 molar acetate, and then we add some hydroxide. Well, all of that hydroxide is going to react with our acid because hydroxide is a base. So that means we'll subtract off 0.01 here, add 0.01 over to the acetate, and we'll set up our ice chart down here below, just like we did previously. So now the initial concentration of the acetic acid is 0.09 molar. The initial concentration of the acetate is 0.11 molar. So we can plug in, and then we get this same expression that we did on the other side, except with some slight deviations. So we have Ka is equal to 1.8 times 10 to the negative fifth. So again, Ka is on the order of 10 to the negative fifth. Whenever we look at the initial concentrations of our acetic acid and our acetate, they're on the order of 10 to the negative first or 10 to the negative second. So we're going to go ahead and ignore this expression right here. We can ignore that x. So whenever we go through and solve for x, we find that the value is 1.5 times 10 to the negative fifth, and the pH is equal to 4.8, and then if we add that next significant digit, it's 4.83. So again, think about this. We start out with 0.1 molar acetic acid. We added some hydroxide, so we lost 10% of our acetic acid concentration. So we lost 10% of it, and the pH only changed by 0.1. So it's very resistant to change in these buffer solutions. So this is an example of the common ion effect. So whenever we add hydroxide, that's going to favor the base. Okay, so this is the base, so it's going to end up favoring going towards the acetate ion there. So since it's favoring the acetate, whenever we start to plug in down here using our Ka, we'll see that our hydronium concentration is going to drop. Okay, because for this equilibrium constant to equal, for 1.8 times 10 to the negative fifth is our equilibrium constant. If we have a larger value in our numerator for the acetate, that means our hydronium concentration has to be lower. Okay, so now let's look at the case of adding acid. So here we're going to start by flipping the reaction, because if we add an acid, it's going to react with our conjugate base. So we'll have the acetate plus our acid yields acetic acid. So here we start out with 0.1 molar again for both the acetate and then the acetic acid, but now we're going to add 0.01 molar hydronium. Well, the hydronium is going to react with the acetate, so the hydronium is going to completely be consumed just like the hydroxide, so we're left with no initial concentration of that. So we're going to subtract off 0.01 here from the acetate and add 0.01 to the acetic acid. Okay, so now let's go down below to our equilibrium ice chart, where we can use Ka for the dissociation of acetic acid. So the initial concentration of the acetic acid is now 10% greater because it started at 0.1. So we've consumed 10% of our acetate. And what we'll see is now that we have a greater initial concentration of acetic acid, we will have a greater hydronium concentration. So you'll plug into this ice chart, just like we did last unit. And now what we'll do is we'll write our expression. Oh, but this is nice because Ka is 1.8 times 10 to the negative fifth, and X is on the order of 10 to the negative first or 10 to the negative second. So we can cancel out these X's again. Now this is a much simpler expression to solve for X. So X is 2.2 times 10 to the negative fifth. Well, and then if we find the pH is 4.7 if we round it. But then if we want to be able to compare it, it's 4.66. So think about this. We've started with initial concentrations that were equal for acetic acid and acetate. Our pH was equal to our pKa, it was 4.74. Okay, now we added hydroxide. We consumed 10% of our acid, our initial acid concentration, and our pH just rose barely. It rose by 0.09 units. Okay, and then whenever we added the acid, we consumed our acetate here and formed more acetic acid. So then we had lowered our pH by a concentration of 0.09. So at any rate, we altered our concentration by 10% in either case of adding acid or base, and there was minimal change to our concentration, or our hydronium concentration. There was minimal change to our pH. So that's where one of these equations comes into play, and this is known as the Henderson-Hasselbalch equation. So what we'll find is, if we start with our initial reaction, so HA plus H2O yields H3O plus A minus. We could write out that Ka is equal to H3O plus times A minus, which is our base, over HA. Well, if we want to solve for the hydronium concentration or the pH, we can cross multiply and divide. So then we end up with our acid in our numerator, base in the denominator, times Ka. Okay, well, normally we're looking for pH. So if we want to find the pH, we take the negative log of everything. So what we'll do is negative log of everything in this expression. So the negative log of H3O plus gives us pH equals, well, the negative log of Ka is pKa. And then, since we'll have the minus the log of acid over base, we're going to actually change that. So then it's plus the log of base over acid. And this should make sense because this will end up being the base is our products over reactants. So this is known as the Henderson-Hasselbalch equation. Sometimes it's useful, but you have to know which particular cases you can use it in. So I typically just use a Ka or a Kb expression like we've done on the last two problems. So here I'll show you one more problem and then we'll probably call it a day. So if we want to calculate the pH in a buffer solution that we have 0.45 molar NH4Cl and 0.15 molar NH3, so we have ammonium chloride and ammonia. So you have two options. You can go through and set up an ice chart. You can use Kb, so we have ammonia plus water yielding ammonium and then hydroxide. Go through, plug in your initial concentrations. Know that this reaction is going to the right because we have no initial hydroxide. Then you could go through and plug in for Kb. Well, we can use the same trick again because our initial concentrations are on the order of 10 to the negative first. And then Kb is 1.8 times 10 to the negative fifth, so we could ignore this x, and we could find that x is equal to 6.0 times 10 to the negative 6, but remember that this is the hydroxide concentration, so you can find the POH, and then from there you can find the pH. The other option is you could use the Henderson-Hasselbalch equation, and this time we could use the base form of it. So if you're looking for the POH, we'd have Kb is equal to base over acid, so it's the exact opposite of what we wrote whenever we used Ka. But you'd put the Kb value in times 1.5 divided by 0.45, then you will get the same initial concentration of our base. The other option is if you wanted to use this Henderson-Hasselbalch, the acid form of it, so we have Ka acid over base. Remember that you could use this Kb value to find Ka because Ka times Kb is equal to Kw. So you could take Ka is equal to Kw over Kb. And then that would give you your Ka, and then you could plug in for your acid concentration. Remember that the ammonium ion is going to be your acid form, and then your NH3, your ammonia, would be your base. So you'd have your Ka value that you calculated times 0.45 divided by 0.15, and you could find the pH directly. So all these ways are equivalent, but it's really personal preference. They should all get you to the same point. All right, so next unit, or the next part of this lecture, we will talk about titration curves. Smash that like button.